Welcome to a tutorial on survival prediction. I'm Russ Greiner. I'm a professor in computing science and a CIFAR AI chair. I'm going to give one of my talented postdocs, talented PhD students, Shangji, who did a lot of exciting work going on. So let me begin by imagine you had this horrible news. You just learned that you have a potentially fatal disease. What is the first question that you would ask? Is it perhaps, what can I do to reduce my risk? Or maybe you want to know, what's the probability I'll live for 10 more years? Or maybe there's a lot of people with the same disease. Of those people, what is their collective probability of living 3 months, or living 1 year, or 5 years? Or maybe it's, how long do I have to live? Quick show of hands. How many people would ask the first question, question 1? 2? 3? How about 4? Yeah, that's a question I would have asked first, right? So let's talk about these different ways to do survival prediction. So imagine you have a whole bunch of patients and you want to know their status. One approach is you could look at the risk score. That's the first question I asked. What's the risk? And you get a bunch of numbers that correspond to a single real value that says what's your risk compared to average. And high risk is bad. You want a lower risk, though, which you prefer. So there are tools which do this. So there's a tool from the disease risk index for example, many diseases. For example, lung cancer. You would answer 10 questions sequentially, and based on that, it will give you a risk score. It says, here's your risk, and here's a baseline. Here's what would happen if you were to stop smoking or to get more exercise, whatever it is. And it's nice. You look at the pretty colors you get, which is nice. But there's some questions like, well, if I were to reduce my risk, if I were to go to the gym every day and stop smoking, would I live for 30 more years? Or would that be 2 more weeks? We don't know. These risk scores doesn't answer that question. It just gives a number. Is it better or worse than average? It'd be better to have a more meaningful value. Let's look at survival probability for a time base. So imagine we look at the probability of 10-year survival. And again, the same 3 people, you get numbers like 38% or 2.9. And again, you want a large probability of living at least 10 years. Well, there are tools which do this also. There's a famous, how many people have heard of the Framingham study? It's a very famous study for analyzing that. It has many different tools, including cardiovascular disease. What's the time until cardiovascular disease? And once again, you answer 7 questions, and based on those questions, it makes a prediction. Here's your 10-year probability. But why 10 years? Why not 1 year or 20 years or 2 months? Why was it 10 years? Well, that's a nice number, but are there better things you could do? I should point out that it says risk there, but actually that's a probability in this particular case. Well, there are another set of tools will look at survival not for a single time point, but for a large amount of time points, but they're for a population. So imagine I had 2 classes of people, men versus women, and I have a population curve for men and one for women. And I can now use this curve to ask about mean time or median time. I'll talk a lot about that soon. And there are tools for that also. The SEER study has a whole bunch of tools for looking at population bases. You answer questions about a population, and it gives you these statistics. This is a survival curve. I'll say a lot about that in the next several slides. So this says, for example, the 5-year survival time, 5-year probability of this particular disease is 11%. So it's not a good disease to get. And 10-year, I can do both those, is 7%. And you live for 3 months or 1 year and get survival probabilities for each one of those. But this curve, while it gives many different values, it's for a whole population. It's not for me specifically. It's for everyone with lung or bronchus cancer, 65-year-old plus males. But of course, it doesn't have any other patient-specific information. And that's critically important to know histology, blood works, single nucleotide polymorphism value, and so forth. So back to the questions I posed. I talked about ways to risk scores, a 1-year survival probability, or population survival curves for the whole population. But most people said they really wanted individual survival tools. How long do I have to live, me in particular? So there are tools for doing that as well. I'm going to talk about that. It's a little indirect. I'm going to start by talking about an individual survival curve or an individual survival distribution. So here, again, for every individual, I would get a survival curve, not for the population, but for this individual. And I can then look at the mean value. So for these different curves, so on that side, you can see the mean values for the first patient is 2.1, there's 8.7 and 3.5. You can say the mean value and say, that's how long I have to live. That's an estimate. And again, there are tools which do this. So for example, if I look at people with stage 4 stomach cancer, I can do this type of analysis and find the median over the population is 11 months. But now here are two patients, A and B, and I look at 40 different blood factors and other information, and here are 3 of them, and I can make predictions. Even though the average over the population is 11 months, turns out Mr. Patient A, he'll live 20 plus months. He'll be able to see his son's wedding. Unfortunately, Miss Patient B, her average or expected value is only 2 months. She should be in hospice right now. So same population, but very different values. And there are ways we can do this. And that's what answers the question, tell me my probability, what's my chance of living? Which again, that's what most people want to ask first. How do you evaluate these models? I'll say a lot about that soon. So this was a motivation. Quick question, how many people know what survival prediction is all about? And why are you here? No, thank you. So we're going to talk a lot more details, but what makes it interesting is something called censoring. I'm going to talk about what that means, and then talk about the typical task, and then talk about models, and then evaluation measures. So, what is survival prediction all about? So, this is a machine. People know machine learning. This is a typical data set. I've got a bunch of covariates describing an individual, and I have a time. And I can now ask questions about what do you do with this data? Well, I might look for risk factors and say, and I'd be able to say based on the correlation of each individual column with the outcome, I can say, for example, being male protects you against this disease, or a high BMI increases your risk. All those are statistics you can compute. That's one thing you can do with it. But I'm more a machine learning type of guy, and I ask questions about build something like a regressor for new patients. So it's a regression task. I want to just predict a number, right? Almost. There's one more column I didn't show, which is a column, the censor bit. That's what makes life difficult. That's what makes us talk different than just standard regression. So what is the censoring? Let me tell a story. Imagine a study started in 1990, a 5-year study. And over this time, we collected people, and some, unfortunately, did not make it. Other people started, not at the beginning, but also, again, perished. And that's too bad. But there are people like patient 3 who, at the end of the study, said, thank you for the study, bye. Other patients, they left the study. Other patients, again, they left the study before the termination, before the event had happened. The first set of patients are called uncensored, because we know when they died, how long they died. The other patients are called censored, typically right-censored, because we have a lower bound on their survival time. So again, the first patient, the study ended, that's why he left. This is a study of how long until someone dies of lung cancer. Patient 5 was hit by a bus. So we'll never know how long he would have lived. He's no longer with us. For 3.7 years, he did not have lung cancer, did not develop it, did not die from it, I'm sorry, but he died by other causes. So this is a type of censoring that could happen. So again, this is the standard figure. Again, I've got covariates describing a patient, a time, as well as a censor bit. I showed here. When I first started looking at survival analysis, I thought, I just point out, the censor bit, if it's 1, it means the time we see is a time to death. The other case, when it's 0, when the patient was censored, at this point, it's a lower bound. We know that, I can't quite read it, that the third patient lived at least 5 years. Was it 5 years in a day or 30 years? We don't know. And the second patient, 3.9 years, at least. Was it 4 years? Was it 14 years? We don't know. When I first started analyzing this, I thought, well, that's fine. I've got 1,000 patients and 5 are censored. Big deal. I just ignore them. Again. it turns out that lots of data sets are highly censored. 70, 80, 90% censored is not uncommon. So you can't just ignore them. You have to treat them effectively. And so standard regression techniques don't work, and you use something else. People tracking so far? So survival analysis. Again, the standard example is time to death. That's what survival typically means. But the same analysis can be, in general, it's time to event. So it could be a time to relapse, or time to re-injury, or time to disease onset. These are all sort of bad things. It could be time to remission, which is a good thing, right? How long until something positive happens? And it doesn't be medical. Time to heart failures, or until a player in a video game advances to the next level. Or imagine you're looking at customer loyalty, and you see how long until the patient leaves, no longer buys at Safeway. That's another type of regression, another type of survival analysis. Or until a customer defaults on a loan. All these are very relevant questions. Or my favorite example is time until students graduate, right? Because there's a time that happens, and it's sort of hard to predict, but it happens pretty soon, right? Okay. The other thing to say is, I now wear survival prediction color glasses. Every problem I look at is survival prediction. Questions like, will Joe get a promotion? Well, that depends on our skills and seniority. It also depends on how long he waits. Is it 1 month or a year? The question is not, will he get a promotion? The question should be, when will Joe get a promotion? Will a particular part fail? Well, it depends on the quality and its usage, and how long are you waiting for it? Again, it's not will a part fail, it's when will that part fail. Similarly, when will customers stop shopping at a store? Again, same issue, is when will it happen? Or when will a patient die of a disease? It's not, will the patient die, but when will that patient die? And you use that analysis, a lot of problems that were sort of complicated because you're not sure whether it was censored or not, becomes very straightforward. We have tools for dealing with that. So it's not when will happen, but when will something happen? So I'm going to use this as a canonical example, a problem I actually worked on a few years ago with some wonderful people who looked at liver transplants. The question is, here's a patient, should this patient be waitlisted for a liver transplant? Or should we just not to bother? And one answer is, you should waitlist this patient, put a list of patients that might need a liver, if the survival time with a new liver is at least 10 years. So again, I'm looking at 10-year survival at least to make that decision. So we need to do this, we need a way to reliably estimate the expected survival time. So I'm going to talk about what type of survival prediction models could be considered and which ones might be appropriate, and also what measures are relevant. How do you actually evaluate them? Because the standard things like L1 loss just don't apply. Kind of, we have tricks making that work. So there's our outline. Again, there are two questions. What are types of models, and what are the relevant evaluations to consider? So I'm going to talk about the first survival analysis and prediction models, and talk about the space of these models, and then give Kaplan-Meier curves, Cox proportional hazards, single-time predictors, and then the one that gives population curves, and then some quick discussion. So first, when I first started reading about survival analysis, I got confused because there are models that did very different things, and I couldn't quite understand how they related, how they were different. And I realized it needs to be structured, so I found out the structuring. One class of models do risk, give you a number. Here's a score that says how good or how bad it is, and where you want, a high score means you're going to die soon, so you want to have a low score if possible. So there's risk on one side, and other models really give probabilities. They say, what's the chances of having, give a probability measure. So that's one distinction. Another dimension, the vertical dimension, is asking, am I looking at one number for this individual? That's the bottom one. Or maybe one number that refers to all time points, or maybe a bunch of numbers, one for each time point. Where you specify a time point, it gives a whole bunch of them. So this is a 2x3 grid to get started. Excuse me. So that's one dichotomy between probability and risk, and then is it for a single time point, is it for a single value for a single time, or a bunch of values? The other dimension is, am I talking about an individual, one person, this person or that person or that person, or are we talking about a whole population? So, and then I can populate this. I talked about the single time predictors, I talked about disease risk index and the CIFAR system. So I've already populated this a little bit. But there's some tools for these tricks. There's Kaplan-Meier, Cox proportional hazards, Framingham and Gale models. So I'm going to talk about that now. People still tracking? Good. Okay. Then I'm going to spend a long time talking about my favorite, the individual survival distributions. So first, the Kaplan-Meier. So I already hinted at this picture. This is a survival curve. Time is on the x-axis, the y-axis is the probability. And every value on every point here will say, for example, there's a 50% chance of living 12 months, at least 12 months. It might be more than that, but that's a 50% chance. And notice at the beginning part, everyone starts alive. So there's a 100% chance of being alive at time 0. And it goes off, maybe to 0, but it goes to some level. And if people know what a cumulative distribution function is, this is 1 minus that. That helps fine, if not, ignored. 1958, Kaplan and Meyer wrote a paper that had 67,000 citations. Who here has 67,000 citations? Yeah, that's amazing. This is a simple tool for estimating these curves. It can be compared to 2 different populations. So for example, if I have a curve for people taking the placebo and the curve for people taking the drug, you get curves like that. Quick show of hands. How many people, if you saw this curve, would take the placebo? Would take the drug? Let's go back. Took the placebo? I would. Look, you live longer with the placebo. But also you can ask about male versus female and give just different subpopulations. And there's log rank tests and score tests that try to determine significant differences. Is this difference just a nuance of the random data selection, or is it really statistically significant? And a test that can do that. And that can identify risk factors like male versus female, or high BMI, or low BMI, or placebo versus drug. Okay, so very valuable. How does this work? Well, I want to compute for population, so I got a whole bunch of statistics about the population, about covariates. There's a data set like that. It's a survival data set. We got this accursed censor bit that makes things more complicated. And we ignore the covariates. It's for a population. So that curve. There's some statistics on how many people died or were censored. Again, I should mention, this was a 2-hour talk compressed down to a 70-minute talk. So a lot of things I had to take out, including a discussion about how you actually do this curve. There's a question at the end. We can go back to that. But for now, skipping the details, a curve like this, you can ask the median survival time for the population, the 10-year survival time, this population, all you can compute. Okay, it's piecewise. It basically goes down in a stepwise function, but there's that curve. Okay, so again, it's for a population, which is great. If you want to compare populations, subpopulations, you can identify single prognostic factors. I mentioned those already. But it wasn't designed to say for Mr. Smith or Miss Jones what's going to happen to those people. It doesn't have any individual features beyond the things that define the space. And of course, that's a major limitation of this model. So that was Kaplan-Meier. Who's ever heard of hazard functions? Okay. Let's talk about hazard functions, including the Cox proportional hazard, which is the canonical example. So hazard function is this guy. This is an interesting idea. This is, assuming you've lived 2 years, what's the chance you die the next moment? So you assume you live to time t, what's the chance that the next moment you end up dead? And that's what, I used to having a mouse here. That's what this is computing. It's saying the instantaneous chance of death at a certain time, given you're alive at that time. So for example, here's the survival curve, but you look at that, and maybe 6 months after surgery, there's a pretty high hazard rate. There's a good chance you're going to die after 6 months, because you see the slope is negative. But if you live for 2 years, you probably might still die eventually, but it's much lower. So the hazard rate can change over time, as you expect. And in case you're curious, the survival function is actually exponential of negative the integral from 0 to t of the hazard function. But you all knew that, right? So that's just a standard little model. So Mr. Cox, Professor Cox, had a paper that has 64,000 citations that computes this. It assumes the hazard rate is this very form. So given a patient described by X, the hazard at time t, the hazard at 2 years for Mr. Smith, it's this form, which is kind of weird. It says there's one thing that depends on time, and X, and some of it depends on the patient characteristics, and they're not the same. So I can look at, I'm going to learn a hazard function that's in terms of a baseline hazard risk, age 0, and that also, that's independent of X. Now, the hazard rate for X, for the some terms. So for example, for age, the hazard risk for age, if you look at this, if I have two people which are identical, but one's 35 years old and one's 40 years old, if I look at the ratio of the hazard function with two people, I'm used to having a little laser pointer. I would point to the h sub 0 of t. That cancels out. And if you look at the exponential of theta of the parameters times x, all those terms cancel out except for the one term that corresponds to the theta k. So theta k, for if age is a third term, theta 3, that'd be a third component, that depends on, that's how important age is to make this distinction. So you can compute how important individual factors are by themselves with a lot of assumptions. This is what's called Cox proportional hazard. It's proportional hazard, the hazard for individual things, don't depend on anything else. It just depends on age by himself and not gender and not height or weight. And so the exponential of that is a hazard of the kth feature. And notice, if that term looks like 0, if theta k is 0, e to the 0th power is 1. It doesn't matter. It says the age is irrelevant. And the way is to say, if the hazard function is close to 0 for a particular feature, don't worry about it. That doesn't matter. So this is Cox feature selection. Okay. Okay, now I got stuff here, and I'm going to skip this. Again, I thought I had a button I can click on the hyperlinks, but I don't have that. So ignore this. Just saying that. So Cox proportional hazard returns a risk score, a real value for every individual. It stratifies risk. And it's useful for answering questions like, will patient A die before patient B? Because if I tell the risk is higher, that means they're more likely to die earlier. So it just depends on this learned parameter theta, the dot product of that and x. So I can compute who has higher risk. I can also find what features are relevant. I can also, we'll see in a moment, I can compute survival curves. I'll talk about that in a few more minutes. But I make some strong assumptions. It assumes that the hazard of imagine I was talking about a gene number 7. The hazard of gene 7 at time 1 and time 2 and time 100, it's the same hazard risk at all different times. And you could imagine, by contrast, that certain features, right after an operation, something might be really important. A certain blood factor is really important after an operation, but over time, it's no longer as relevant. But the hazard function, proportional hazard means it doesn't matter. It's all the same for all time. That's a major limitation. It also assumes that features are independent. That's this linearity assumption. That, again, is a strong assumption. You can't have that age being really important for men, but not for women. You can't say that because it's a linear model. We're going to see in a moment that the curves you get don't cross. I'll show it later on. So that's the second model. That's the proportional. On to the third thing, individual signal time predictors. I already mentioned the Framingham score gives a probability for 10 years. There's a Gale model. People heard of Gale model? People who do breast cancer research have heard about this for onset. It estimates the probability a woman will develop breast cancer within 5 years based on a few questions. There's a predictive pressure model developed in Calgary that again predicts probability a subject will develop a major depressive episode in the next 4 years based on a small number of features. I've also been involved in some projects, a 30-day readmission. The probability of a 30-day hospital readmission using electronic healthcare records done by Sasha Davis, who's another brilliant student, did some wonderful work, and looked at the fact that I had multiple time points to look at for electronic health records. Prostate cancer recurrence, looking at 5 years after diagnosis based on H&E stained tissue microarray. Again, Matav Farouk did this work, and a lot of cool stuff there. So now, that's all background. Let me talk about the most interesting part, the tool that we developed here, the individual survival distributions. So again, I'm assuming a background probability enough to know what a S is a random variable for time to death. It's not greater than time to death. There's a chance a person died at 2 years, at 2.7 in 3 years, and it's some sort of curve. That's a probability distribution function, PDF. Now, survival function chance of dying after a certain time. Well, what does that correspond to? Well, that's the integral. The chance of dying after time 4 is just the integral of all the values from time 4 on. This is a simple probability distribution function. And okay, that's what I want to say about that. Okay. So now I can quantize it. I can, instead of individual time, instead of having continuous time, I can say let's quantize it. Let's have individual time chunks. So I might make it at times 2, 4, 6, and 8. And now the chance of dying there would be, well, I can just find buckets and say these are probabilities. They all add up to 1, but they're all non-negative numbers up to 1. And now I can say the chance of dying after 4 is a probability mass function, not a probability distribution function. It's just the sum of those two. Okay, everyone's tracking this? A little bit of math, but it's not that hard. It's just that sum of those two values. Now, of course, the time points don't have to be uniform. I can have any intervals I want, like 2 to 4.5 to 6.9 and so forth. And again, the same thing, I just had to add up the points. Okay, skipping a few of the details. So now I'm building what's basically a multinomial distribution for every individual. I want to map to some probability distribution over, in this case, 4 values. Excuse me. So now the probability of dying in the 4th interval after time 7 means I must have been alive the first time. So if you think about that, it means I die in the 4th interval. I can look at this. This sort of a proof by PowerPoint. You can just say that I'm going to add them up the wrong way. I'm going to say the chance of dying in the last interval is there. Chance of dying in the 3rd interval means you didn't die in the 4th and died in the 3rd, and so forth. So I get a curve like this. This is how I build the survival curve. I'm going to build a multinomial distribution and add them up the wrong way from the last time onward. And then I draw a pretty picture by smoothing it out. And that's our survival curve. Lots of tools which do that, and we developed one of them, and I'll say more about that in a moment. So again, what's a trick? I've got a bunch of parameters, one for each time, and now I'm going to build a multinomial distribution. I already said all that. Okay, just keep going. So what's the basic idea? You have a patient, you have an individual survival distribution ISD model, and it produces a curve. How do I get that model? Well, machine learning 101, right? Give me a labeled data set. Survival data set, you notice it's got the censored bit there, and I now have a learning model that produces this. Some of the benefits of these tools, one of them is, remember that problem with censoring about I don't know what happens after a certain time? That's easy. Imagine someone was, again, there's 5 time points. Someone was alive at 1, alive at 2, was censored at the 3rd time point. So when did this person die? Well, I don't know when that person died, but maybe he died in the 3rd time and stayed dead. Or maybe he was alive the 3rd, he died in the 4th. Or maybe he died in the 5th, or maybe he stayed alive to the very end. These are all the possibilities. This is the no zombie rule, right? If you're alive, if you die in the 3rd interval, you're still dead in the 4th. Everyone agree we shouldn't have zombies? I think people tend not to model that point. So it's very easy, very natural to handle censored data. And that's the nature of these survival challenges, survival prediction challenges. You ask questions like, what's the median survival time? That's just what crosses 0.5. That was easy. And you get certain, so here it's 45 months. Yep. Okay. Or you can get like confidence intervals around that correspond to between 25 and 75 and so forth. Okay. Another benefit is you can compute the expected value. What's someone's expected survival time? And that's a very simple form. What is the expected survival time? It's the chance you die at t times, it's t times the chance you die in t. Well, that's very easy. So it's going to be, it's p of time d1, the first interval, times 2, because that's the size of the interval. I wish I had my laser pointer. So it's p1 times 2. And then it might be in the second interval, which is 5, which is the width, times the chance of dying in the second interval. And it's 7 times the third interval, and so forth. Just the sum of those blocks. That's exactly what integration is. The mean value is exactly the integral of this curve. What could be easier? Okay. So there's a very simple way to compute the mean survival time, which is what we're going to want for our task. I want to tell what's the expected time. Expected time means mean time. How long is I expect them to live? I've got the information in front of me. So a very clever, a former postdoc, Amii, sort of introduced me to this whole area in a very clever way, something called multi-task statistic regression, that basically learned a simple model. I'll skip the math. It's just saying there's a very simple way of doing it that had a very simple partition function and you got this probability, and it works amazingly well. Okay. And one more little trick, the optimization. He imagined having a normalization term, I don't want the problems getting too big, and a smoothing term, where smoothing means whatever kills you in the third time is probably the same that kills you in the fourth term. So the parameters should be similar. So he had this other term, but then another brilliant master's student a few years ago said, no, you don't need that term. The regularization is sufficient. I didn't believe, but no, he's right. So the problem's even easier. This function is convex and differentiable. You can initialize the parameters very easy. You use EM. You can find the single parameter by internal cross-validation. And how many points do you get? Well, we did empirical studies, and if I have 100 points, choosing 10 partitions makes sense, the square root of it. And the partitions are not based on clock time, but I want the same number of deaths in every one of these 10 partitions. Okay. Okay, same thing with it. So again, these tools are very nice. I mentioned quickly, I talked about Cox. I said with Cox, you could build a survival curve from those bad boys, but they look like that. They all look the same, because there's one term that says, here's Mr. Smith versus Miss Jones versus Mr. McGillicuddy, and that describes it, and then everything's just scaling it. From that point on, it's just scaling it. So the terms all look the same. Whereas in our models, time and covariance can interact in ways, and you get things that cross, and all sorts of more interesting characteristics, which end up being more accurate, more valuable. Okay, so that's the final model I introduced. Let me say a bit about a discussion. The survival analysis and survival prediction. Survival analysis, in my mind, is finding prognostic factors. It's finding biomarkers. It's saying, yeah, age makes a difference to this person, but gene number 7 doesn't. And there are tools like Kaplan-Meier for doing our Cox feature selection. Finding prognostic factors, you evaluate by looking at populations, and you can use it to prove drugs or to decide about medical devices. By contrast, survival prediction is prediction in the machine learning sense. I'm trying to actually figure out, build a model for an individual. So MTLR fits in this model. So do things like risk models and prognostic scores and so forth. You evaluate by looking at individuals, seeing how good the models are individual. Okay. An overview, a summary. The risk model, so here's 3 patients. They have risk scores. They have like 5-year prediction numbers, which are probabilities. They have group level survival models, which is for the whole population, all these individuals, and the individual survival models. And so the risk questions are good for, is my risk higher or lower than average? Is my risk more than his risk is? Okay. My caricature is, again, you've been told Mr. Smith told you he's about to die, and his first question is, oh, that's terrible. Will I die before him? That's not what most people would ask. So that's what you can do with that. What's my 5-year survival probability? What is the average for the population? I'm sorry, average survival for 5 years or 10 years. What's the median survival over populations? And finally, this one is for my survival probability, or my median survival time. All this can be done with the final model. Okay. So back to the question I motivated, this wait time for a liver transplant. You want to look at the expected survival time. So to do this, with a risk assessment also gives you a single number. Is that the number you want? And it doesn't tell expected time. It doesn't even give risk. It's just based on time-dependent. You need something that's going to give time-dependent information. So forget that. What about these population models that give the same probabilities like Kaplan-Meier curves? Well, again, that doesn't work either, because I want it to be individuated, not for the whole population. I want to know for this population, this individual, what happens. So forget that part of the grid. What about single time points? I want to know about 3-year survival or 5-year survival. Well, again, I don't want to know about 5-year. I want to know about all the different time points to make these predictions. I need to be able to integrate over them. But maybe you say I could do a 5-year model and a 10-year model and a 3-year model too. You could do that, but you have this problem. What happens if the 1-year model says there's no chance this guy lives more than a year? And then the 2-year model says, oh, 30% chance they're alive in 2 years. Anyone see why that's a problem? Remember those zombies? We don't do zombies, right? You can't have, if you're going to be dead in 1 year, you're not alive in 2 years. So again, we have individual models not sufficient. We need that, again, eliminates these other models. Look at single time points. So we're left with the one I encourage you to look at, the thing that looks at probability values at multiple time points that are actual probabilities. Okay. So again, you can use it for my weightless computation. Again, I can look at this curve and say the area of the curve is 14.2. Yes, it's more than 10 years. I like this patient should get a liver. This guy, 3.6. Nope. I shouldn't give a liver to this person. Other people would live longer with one. This guy, I also would give. Quick comment for people who are squinting at this. You might notice that the 10-year survival probability is less than a half. The area of the curve is still 10.4, even though that individual 5-year survival probability, 10-year, that would not be sufficient. Okay, so again, back to that model. Okay. Another quick comment about this ISD framework. Given one of these models, if someone says, but I really want a risk score, that's what I really want, well, I can do that. I can just look at the mean value and use negative mean value, I want high values to be bad, to correspond to a risk score and use that, or the median value, or the 1-year survival value. Someone says, I really care about 3-year probability. That's what I really care about. I can do that also. The model, just draw the line at 3 years, and there's my model. I want to do population average. I just look at a bunch of these and take the average. So I can do all the tricks I wanted earlier by this one framework. That's why I like it so much. Okay, everyone tracking? So I've said, here's a whole bunch of things you can use, a whole bunch of things you can play with, and here's what I like best. But now, this is a tutorial. What do people do? How do people evaluate survival models? What are the tricks they use? And point out quickly that if this was regression, it'd be L1, or maybe it'd be like an L1 loss or L2 loss. It isn't regression. Those don't work. Well, they do kind of work. We'll see some tricks later on. Let me talk about how people evaluate survival models. So one trick is called concordance. So imagine here's a MELD score. This is a score that's used for looking at liver transplants. And imagine this was actually the actual time of death. These are, forget censoring, this is when individuals, patients died. And we see that, that the scoring, it's rank ordered by MELD score from highest to lowest. And the order that we see is kind of similar, but not quite. So let's look at the patient who actually died first. If I did it right, that patient would be the first person who died of all 5 of them. So certainly, he died before patient 2 did. Perfect. He was supposed to die before patient 3 did, but did not. That's a bummer. He died before 4, and he died before 5. Okay, so out of the 4 chances, 1 was compared to something else. 3 of those 4 times he worked. What about patient 2? Patient 2 died before 3, before 5, but not before number 1. They approve of patient 2 as well. And patient 3 died before 4, and patient 4 did not die before 5. So out of the 5 choose 2, out of the 10 different possible comparisons, 7 times the right thing happened. So concordance is 7 out of 10. Okay, you look at risk scores for arbitrary risk scores. Okay, point out. If you have censored patient, it gets more complicated. So how do I compare censor? Well, imagine I got patient A who actually died. B and C were censored. Patient D died at time 4 and so forth. For patient 1 who died, I know patient 1 died before B, C, D, and E. So I can compare those. I know what happened. And either it was right or wrong, but I know the answer. Patient B, I'm sorry, he died at time 2. Did he die before patient at time 3? We don't know. One was censored 2, one censored 3. Maybe it's the same order, but it could be other order. We have no idea. We don't know. Is a number greater than 2 also a number bigger than 3? Well, it could be. It doesn't have to be, though. We can't compare B versus C or D or E. We can't look at patient B at all. And the same for patient C. Patient D, we know he died before E. So we can look at how many different comparison points. And so if you put these together, you're going to look at all the ones you can compare, the ones which are comparable, where the first patient died, I can look at patients, I think the next slide, I can look at patients I and J if I was uncensored and occurred before J. Otherwise, I can't look at them. Okay. So C-index is called C-index is most common. I don't know why. It does this application if I have one ICU bed at a hospital. Who should get that one bed? Let's give it to the sickest patient, one who's going to die first. So I can imagine a rank order for that. I want to choose amongst actions for a patient, which one has the highest risk of dying? Well, don't do that one. Go with the least risk. That would make sense. That would make sense. Okay, but again, for both, I want high concordance. I want to know the ordering was correct. Kinda. Let me point out that as orderings in general, I probably care about number 1 and number 2. If I get that wrong, I might give the hospital bed to the wrong patient. And maybe number 3 and 4, maybe those matter. So I lose a point if I get 1 and 2 wrong or 1 and 3 wrong. What if I get number 101 and 102 wrong? That counts a point also. Do I care about those? Well, I only have 1 hospital bed, so it really doesn't matter. So there's some problems with that. There are tricks like taking log ranks and so forth. Okay. Next, Breyer score. This is a score that looks at survival looks at a single time point. If I give a single time point, this form is complicated. Let me show an example. Okay, so I care about 15 years. That's what I care about. And now there's my survival curve, and the patient actually died at that time. So I can now say the patient died after 15 months. So he should be alive. He's alive at 14 months. So I should have been 1. That's what it probably should have been. But I predicted 0.52. So that error squared is the error. So if someone who is if at a certain time I care about, the person died after that, like I look between that and 1. About this patient who died before that. Well, so he died before that time, so that's the error. He should have been 0 at that point, but actually it's a difference, it's a 0.75 squared. Okay, kind of mathy. There's a way to deal with censored patients. I won't talk about that. There's integrated Breyer score, which just takes us and integrates over time. Again, I'm going a little bit faster, just showing it's just taking the square points and just that green area. Okay. Some notes. The Heaviside function is great. You can do that, you get 0 error. If you get the right point, which is what you want. And notice that if you just choose a point at 0.5, that predictive model, that stupid model says everyone has a 50% chance of dying at time 0 and goes on. That gives a Heaviside function of 0.25, wherever the person died. So that's kind of that's a degenerate opposite value. All right, keep going. One calibration. So imagine as a weatherman, and every day the weatherman gives a prediction about the weather tomorrow. And imagine he says 60% chance of rain tomorrow, and he says that 5 times. So what's the actual weather? If he says 60% chance of rain tomorrow, and does this 5 times, you expect, but because 60 is greater than half, expect it all 5 times? All 5 times? No. 60% means 60%. It means if he said 60%, it should rain 3 out of the 5 times, right? That's what it means to be calibrated. So it should be this second model. And again, if he says 20, if 100 times he says 20%, it should rain 20 times out of this 100 times, and so forth. Make sense? Okay. So what about these funny curves here? Let's imagine I care about 30 months. Just get rid of all curves. Look at 30 months. I can do the same sort of idea. I'm going to look at the 30-month probabilities, and I can bin them. So the first 5 patients, the highest values, second 5 and third 5. And now imagine those 5 values, if you look at them carefully, and add up those average values, you get 78%. And then it turns out those patients, actually, in truth, 4 of those 5 patients are still alive, so 80%. The second cluster, the average was 45, and 3 out of the 5 were still alive. So, in the third one, it was 17%. So again, if I did it right, if it was calibrated, those numbers should be the same. For the first cluster, the first bin, it should be 78%, and it's pretty close to that, but ideally, it should be the same numbers-ish. Okay. So how do you evaluate it? Again, I'll skip the details. I'll just show you a picture. Use 10 buckets. You want bins like this, where you can see that for the first one, the numbers are about the same. The predicted and absolute are about the same. For the second one, they're far different. This is called the Hosmer-Levenshaw test. The statistical tests say do you believe that's caused from the same distribution? Okay. It's using a calibration. There's tricks for dealing with censored data by just taking the 5 patients and not looking at the numbers there, but building one Kaplan-Meier curve for those 5 patients and looking where that crosses 30%. Okay. You can make individual decisions and so forth. Okay. You can accurate number of deaths. It's a statistical model. If it was calibrated, you now can use it as if it's a real probability. Insurance company can use it to set premiums for different individuals at a certain time point. It's a limitation one value. Whew. Okay. Next model. Decalibration is a pretty standard thing, so that we invented here. Looking at individual curves and saying what does it actually mean. Can you trust it? So let me talk about this model. So here's a Kaplan-Meier curve, one curve for everybody. From this curve, it has the same distribution for every patient. And so I'm saying the median survival time, in this case, is 20 months. 20 months is when the median time is. And now if a patient dies of DI, I can say, if I have 100 patients for this population, oh, I gave the answer away. Oh, you didn't see that, right? So if I did it right, there's 100 patients. How many should die before the median time? Median means half. Half 100 is? Now you can read what that number is. So that's what it means. So basically, the number of patients who died before the median time, whose probability of death is greater than that, should be 50%. I'm going to be a little faster. I got a lot more I want to cover. I'm just saying that there's ways you can look at that. And so you can, there's nothing special about 0.5. You could have, 75% should die before in 8 months, and 25% should live at least 52 months. The same idea. So basically, you're saying this formula here at the very bottom is saying, basically, if I look at the probability of each person's death, that should be uniformly distributed over 0 to 1. Make sense? I see one nodding head. Thanks, Jeff. So MTLR, again, now we have multiple time points, multiple patients. Again, I'm going to go faster. You just look at the median. Every patient has his or her own individual median time. And again, if I did it right, how many patients should die before their individual median survival time? All of them, right? 50. It should be half of them, right? Same idea as we had earlier, just with subscript I and so forth. So that's what. So it should be that for the ith patient's distribution associated with the ith patient's time to death, that should be uniformly distributed. Okay. And so you can make that prediction. So that's what it means to be decalibrated. You can show some examples by showing that these are 4 patients, and each one had time of death. And sure enough, for the 4 patients, each one died in 1 of the 4 quadrants. Imagine I had 20 different quadricyles. I can look at 2,400 patients and see they should all be about 5%. Okay, I'm going to go a bit faster and just say there's a chi-square test for this and so forth. Okay, the ways to handle censoring, I'll skip that. Applications, you can ask, whereas one calibration is really good for saying, I want to know the 1-year survival or 5-year survival for a patient. What if I say, Mr. Smith here, he wants to know a number such that he gives a premium. If he dies before that premium, his individual premium, what should be the factor of 2 return? What should his premium be? Well, if Mr. Smith's median survival time is 7.2 years, then the fair premium for 2 times return should be 7.2 years. Okay, blah, blah, blah. Skip that. Just lots of different tests, things going on. Okay. So one calibration is over time. Decalibration is over probabilities. Okay. So everything here is preliminary. Now let's talk about what you really care about. I really care about mean absolute value, and I've got an expert who's going to talk about that. Xiang. I get this.
Thank you, Russ, for introducing me, and thank you everyone for having me. So let's continue. Survival analysis is pretty much like regression, with only issue or main concern about censoring. So a natural question can arise: how about we directly use regression metrics that we commonly use? For example, the mean absolute error. The mean absolute error calculates errors between the predicted time and the true times. So there were a few challenges for directly applying these metrics to survival analysis. So first of all, how can we calculate the predicted time from an IST curve? So there are several options, which Russ have already covered some of them. So we can use the mean survival time, which is the area under the IST curve, or we can use the median, which is the time where the IST curve just surpassed the 50% probability lines. And the second question is, what is the true event times for everyone? So for uncensored patients, it is easy, this travel. We know the true event time for them. However, how to handle this for censoring subjects? We only know the sensing time and do not know the event time. So it turns out there are several methods that can handle censoring in calculating Amii. So the most naive method, possibly, is to simply exclude all censored subjects from the data set. And you guys can easily see the limitation about this, right? If you have a high sensing data set, then you're ending with a small biased proportion of the data set that, and your model is evaluating on that biased samples. So another metric is called Amii hinge. So hinge score calculates the error if the predicted time is before the sensing time. So to illustrate the idea, we have 3 patients in the diagram here. So for patient 3, let's say his predicted time is at here, which is ahead of his censoring time. Because his event is later than censoring time, so we know the error is at least as much as the differences between the sensing time minus the predicted time. And for patient 4, our predicted time is later than the sensing time. In this case, the event time, we do not know the true position of it. It could be some errors, but we cannot measure this. So what's the lowest, or what's the possible errors for this case? Zeros, because we don't know the true event times. So for this patient 4, we give them a 0. And for patients 3 and 5, which the predicted time is before the sensing time, they have some source of errors. However, you can also see the limitation of this method. This method is an optimistic score that only considers the minimum possible errors. So now I'm going to talk about a few desensing methods. We call it desensing method, and some other people didn't call it this way. So desensing method try to solve this challenge by replacing this sensing time using a surrogate value. So the concept is, since for the censored patients, we already have some knowledge about them. We have a censoring time that we know they at least survive until there. So we can use this information and other informations in this data set. And we can come to a surrogate value that estimates the true event time for these censored subjects. And then we can use these surrogate values to replace the original calculation in the Amii calculation. So the first matrix in this family is called Amii margin. So let's say this is the predicted curve from the model, and this is censored subjects, of course. So the idea is we take from the Kaplan-Meier curve that Russ introduced before. It is a marginal estimator for the for the survival distribution. And then, because we know this sensing subject has lived as at least 20 years old, therefore, we extract the subsequent part of the Kaplan-Meier curve, which is only this part. And we're going to do a renormalization for this curve. Yeah, renormalization for this curve, so that this curve starts with 100 probabilities. So this renormalized curve is called conditional Kaplan-Meier curve. And then we can calculate, for example, the expected survival time from this curve and use this expected conditional Kaplan-Meier time as a surrogate value for calculating the Amii. Another idea is called IPCW, Amii IPCW. So Russ barely covers the idea of IPCW, but I will cover it again. So the concept is, for censored subjects, we're going to transfer the weights for these censored subjects to its subsequent uncensored subjects. So to illustrate the idea, I have 5 example patients. So this C2 is a censored subject. And we can approximate this event time using the uncensored subjects after him or her. So in this case, there are 2 uncensored samples after C2, and we can use an average of these 2 samples to approximate the true event time for C2. And we use this surrogate value to replace the MAE calculation in the original form. And the last one, which is the most powerful, we find, though it is the most powerful one, it's called MAEPO. So MAEPO also calculates the surrogate value or desensing value using the idea of pseudo observation. So idea of the pseudo observation calculates how does a censored subject contributes to the overall Kaplan-Meier curve. So to illustrate the idea, we have this same 5 subjects. With the first step, we calculate the Kaplan-Meier curve for these 5 subjects. And then, let's say our target in our interest subjects is still this censored subjects at the second place. We remove this censored subjects from the data set and recalculate the Kaplan-Meier curve again using the rest of the 4 subjects. And then we compare these 2 curves and calculate the mean survival time from these 2 curves. And then we can use the JACNAF estimator to calculate the surrogate value. So the JACNAF estimator calculates is as the following: the number of subjects times the unbiased estimator of all subjects minus the n-1 subjects times the unbiased estimator of the n-1 estimators. Okay, so anyway, this fancy little equation gives you an approximated score for this case, and you can replace the MAE calculation using this score. So for this decensoring method, remember we calculate the surrogate value. I always said it so many times. However, some surrogate values are more confident than the others. Therefore, we should weight the censoring patients based on when they got censored. So let's say if a patient is censored at the very earlier time 0, then the possible range of his event or her event time could be from 0 to the end of the study or infinity. Therefore, the surrogate value we're given is very unlikely to align with the true event time. However, if the censor is close to the end time, then the surrogate value we're calculating is probably close enough to their true event time. Therefore, we should give them a higher weight. In this case, we use the weights as 1 minus Kaplan-Meier curve as the censoring time. The idea of this weighting is the probability of being censored at C1, which is the censor time for these subjects. And for uncensored subjects, of course, everything is known, so they got the maximum possible weights, which is 1 or 100%. So we can plug in these weights to the original MAE calculation. Of course, we need to examine which MAE variance is the best. So we examined the MAE variance using 2 criteria. The first one is how they align to the true MAE. And the second is how they rank the model correctly, or whether they rank the model correctly. So I'm not going to go into the detail of this evaluation. However, we create a realistic synthetic data set that can have real features, that also real death times and close to real sensing times. And empirically, we find that the MAEPO, which is the last evaluation metric for MAE family, that works the best significantly compared to others. And if you're interested at the papers, you can scan this QR code. Let's back to Russ.
Thank you very much. So again, lots of good. I mentioned Xiang did almost all that work for that stuff. There's a whole bunch of slides we're skipping that show the clever ways we had to evaluate the quality of the different models. Okay, I'll make the slides available later on with that. So summary of measures. So we considered many different measures They're fundamentally different. They're measuring different things, and for example, there's 5 choose 2. And I think, okay, good. So again, another set of slides we're skipping is the actual way to show that they're measuring very different quantities. That L1, one calibration and decalibration are different things, and they measure very different things. Let's keep going. So which measures should you use to identify the best model? Well, it depends on your task. Instead of saying, I've got this cool tool to evaluate, start by saying, no, I've got a problem to solve. What is that problem? And that problem should dictate how you evaluate it. Okay. And so everyone uses C-index. That's every paper you write has to have it. And I don't know why, because it doesn't make sense for most problems. But let me say a bit about what type of problems lead to what type of measures. So who gets the next available ICU bed? For this problem, sure, C-index concordance makes sense. Who's the sickest? Give that person. I got it. That's fine. Who should be in a hospice? Well, if I've got 5 patients, this one's the sickest, and that patient's still going to live 30 more years, no one goes in the hospice. If I've got 5 patients and even the healthiest of those patients is going to die in 2 months, they should all be in the hospice. It should not be C-index. The ranking doesn't matter. They want a time to event. If you have time to event, then looking at Amii or some version of it makes sense. I want to quantify. I've got a patient, here's treatment A, and here's treatment B. Does it make a difference? I might want to try ranking them, but more importantly, is it worth the additional expense to do this additional procedure? Again, time to event. Looking at the time to event for A versus B for the same patient. For life insurance premiums for a fixed time, like going to 5-year insurance across people, one calibration makes sense. Horizontally, if I have an individual patient, I want to know for that individual, what time should I use to make a premium for that individual? Again, in this case, I would choose a decalibration. For Brier score, integrated Brier score, I've challenged my colleagues in the survival community. Tell me a reason why I want to use them. Well, it's cute. It looks pretty. No, give me a reason. No one's done that, but maybe you guys can find one. If so, we can include that. Okay. Next, we did an empirical study, a whole bunch of things that we tried to evaluate different things. Oh, I bet. See, when I made the slides, I thought I'd be able to click on the summary slide here. But now, okay, you guys get to close your eyes. I'm going to go through about 30 slides right now because they didn't give me the button. Guys, this is a lot of hard work that people did. Things converging, didn't converge. You tried a bunch of data sets. You tried a bunch of things. Okay. All right. Keep going. Okay. Almost done. So again, I thought I'd be able to skip all this. But again, we're looking at different models and saying who's winning. And the bottom line was we tried a whole bunch of different models that people have published and used. And after all this work, my thumb's getting tired. We found that 8 different data sets, 7 different types of models. We looked at high censoring, low censoring, high dimensions, low dimensions. That for calibration models, for discrimination models, it turns out that MTLR was pretty much the winner for almost all of them, or tied to be a winner. So again, I like that model a lot. I mean, I didn't invent it, but we got empirical evidence that shows it works really well. Okay, so let me now go on. The discussion point here. Okay, again, I was going to skip these things. A whole bunch of other slides. Again, I thought I was going to have. So I'm going to skip credible regions. Yeah. Okay. We did a lot of work about looking at different types of feature selection algorithms and different tricks for that, and ways to improve on it. And again, I'm sorry. I thought So extensions. One extension is different types of ISD models. So there are models which are parametric and non-parametric. If you use this framework of building, of starting by talking about discrete values, or talking about a multinomial distribution, right now we have like a logistic regression model. You can put a neural net there and have an arbitrary function to learn each individual multinomial term. The Cox model had this exponential of theta. You can make that a neural net model that takes a parameter. Again, we're still separating time from covariates, but again, you can play that game. Another issue is discrimination versus covariant. I talked about this term earlier. So many people talk about different models and say there's discrimination models which try to see who dies first, like C-index measurement, and this calibration, which is, are the numbers meaningful? And it turns out we looked at a whole bunch of different models over the years, and we found that in general, models which do really well for discrimination do very poorly for calibration, and vice versa. Can you optimize both? And Sheng had some bunch of cool stuff there, but I think we don't have time for that. Again, I was going to skip it. Sorry, Sheng. I was supposed to skip this, right? They didn't tell me. So you got this one cool. Look at the graphics, right? It's all these pretty pictures, lots of hard work. But there's ways that he figured out of how to take a model that you learn to try to optimize a C-index or any discrimination, and then you can make it calibrated. That's amazing. Brilliant guy. Looking for a job. Anyone has any? Okay. Brilliant guy. Okay. Let me start to say other things. We talked about censoring. So I talked about uncensored and right censored. Are there types of censored, Professor Greiner? Yes. You can imagine left censors. You call a phone number and say, is John there? He died. When? I don't know. He's dead now. When did he die? I know he's dead this time. When did he die? Instead of having a lower bound, I have an upper bound. And there are ways to use that. There's also interval censored. He was alive now and dead then, and I don't know when in that interval he passed on. So there are ways to take MTLR and other multinomial models and just try to marginalize out certain things and deal with all those. And now you get a chance to talk again for 2 minutes.
Okay, thank you. So here could be a little bit messy and conceptualized. So through this tutorial, we've been talking about lots of models and lots of metrics. And the most fundamental assumption for this model and metrics could be somehow unrealistic. This assumption is what we call random sensing assumption. It assumes the time to event is independent of the censoring time. Let's say the event time will occur, the target event will occur is death due to cancer. And we have some bunch of features we observe, we collected that be helpful to predict this feature, to predict this event. And you can easily see that this event is the direct cause of the features. However, let's assume if the censoring could be cause of hit by a bus or administratively drop off the study, we can fairly assume that this censoring has no relationship to the features we collected and also to the time of event we're observing, because those seem pretty random. However, in a more realistic world we're probably living in, we're having this independent censoring assumption, which means the event and censoring is independent if we're observing the features, if we're conditioning on the features. So let's say the event is still death due to cancer, and on the other hand, censoring could be some other causes. Let's say it's another competing risk cause, which is death due to cardiovascular diseases. So in such case, if we collect a bunch of features involving lab measurements, for example, blood pressure, this blood pressure can be a direct cause of the event, and it could also be a direct cause of the censoring. However, the flow of event and censoring will be blocked if we observe all the features. So in another type of censoring, which is most relaxed assumption, another type of assumption, which is the most relaxed assumption in survival analysis, is what we call dependent censoring. That means the time to event is not independent with the censoring, even we observe the features. So this could happen if we have some unobserved confounders. So let's say gene factors could be a direct cause of both time to death, the death due to cancer and death due to cardiovascular disease. Because genes are hard to incorporate or expensive to collect, many analysis didn't involve it. However, if we do not involve it in our observed features, the flow between event and censoring didn't got blocked. The flow still existed due to this unobserved confounder. So right now, we're finding some solutions that using calculus to jointly estimate the sensing and the censoring and event times. And we're making some progress on that in both modeling and evaluating. However, this is in early stage, and right now back to Russ.
Okay. All right. Some quick applications, just to say that I'll be done. Got to skip all the details, but we looked at trying to model again back to genes, looking at genes to try to predict what type of how long some of the type of cancer will live. And again, lots of details I'll skip, but just saying we're using topic modeling as an approach to reduce the dimensionality from high dimensional space of 20,000 cancer different genes to I think 30 dimensions, these topic modelings, 40,000 down to 30. And then we used MTLR, this tool I mentioned, multi-stage regression, and built a really nice model that looked at both breast cancer as well as kidney cancer. There's a URL for that. We then extended this to use non-negative matrix factorization, looking at multiple different types of cancers, looking at 30 different cancers, finding a 100-dimensional term representation, and used that to learn ICUs over 20 of the cancers which are prominent. And again, lots of details here that work quite effectively as well. We looked at, remember the problem I mentioned about who should be waitlisted for a liver transplant? We built a tool that actually is deployed and people can look at right now. Facts about the individual and about a potential donor. We can look at this individual and look at a lot of statistics about 1 and 2 and 5 year olds, also the mean survival. So this patient would probably qualify, probably should be waitlisted. This patient, however, with a mean time of 9.5, maybe should not by the same criteria. But at least we have information about how long we think this patient will live. We looked at many other applications. Some other things, we looked at predicting time to all-cause death from ECG data with some people in the cardiovascular group. A lot of projects about time until, not breast cancer death, but breast cancer onset. And work that Xiang and other people did, trying to look at perhaps adjustable health and lifestyle issues. We're also looking at COVID cases. You guys remember COVID a few years ago? Can we predict the time to death and also time to discharge? So good or bad outcomes. We've got some really good models for that got published as well. Another one, final example, is very different. I mean, I look at medical applications. Let's imagine a business application. So here's a challenge. I want to know someone's reservation price. That's how much you think something is worth. If I knew what you would think something is worth, I could offer it to you at that price, you'd buy it. That's very important, but you're not going to tell it to me. Can I learn that? If I describe an object and a person, can I figure out that person's reservation price? Why am I mentioning that? So suppose I want to sell this pen. I go to Abe and said, you want it for 10 bucks. And he buys it for 10 bucks. That's great. What was his reservation price? He bought it for $10. What if I offer 12 or 15? I know that it's at least $10, but maybe it's $30 he would have paid for it. Oh, I know that's a lower bound. He bought it for at least 10. Now, I take the same pen and I go to Bob and say, you want the pen, Bob? $7 for you. And he says, no, I don't want it for $7. What's his reservation price? He didn't buy it for 7. Maybe he would have bought it for 5. Maybe for $0 he wouldn't have bought it. That's an upper bound. So these are censored data. The first was right censored. The second one's left censored. This is censored data. It's not time to death. It's price of an object. So can we use survival prediction techniques for that? And the answer is yes, we could. We built a data set using Mechanical Turk to get a bunch of people looking at chocolate and try to evaluate. We got from the transaction and non-transactions. We built a really good model. This is work by Pinjen. Got a publication for that. All right, let's conclude. There's a web page here. Get the URL for that, because this one has a whole bunch of stuff. All I know about survival prediction is summarized on that page. It's got tutorials. I'll put this tutorial if I get it there. It's got ISDs. It's got pointers to papers, presentations, codes, and websites, including his wonderful GitHub repository. I've been so fortunate being in Alberta. I get amazing collaborators in the medical school and people in the math stats, business, computer science, medicine, epidemiology, neurology, nephrology, oncology. I'm reading pathology, endocrinology, cardiovascular. And I get some of the best students in the world, right, to play with all these problems. And this is just a subset. If anyone's in the audience who's one of my students, I didn't have a picture of you, I apologize. It's been great. You guys contribute things I would never thought of and do amazing jobs. Contributions, what am I doing? So I introduced survival prediction and analysis of prediction. I talked about a space of approaches. So again, this is a tutorial about the breadth of things going on. Kaplan-Meier and Cox are terms everyone in survival prediction has to know. I motivated and summarized some evaluation criteria, including MEPO, which was his idea, that works really amazingly well, and I empirically evaluated a bunch of things. And I'll end there. I have time for questions. Well, I've got -5 minutes for questions, but that should be plenty of time. Questions? Yeah. No, I don't. No, yeah, mine died.
Okay.
You died. Okay. Sorry.
Speak louder then.
Can you hear me?
I hear you now.
Oh, I can hear myself. I'm taking this off.
Okay,
It's
but
weird.
He can't hear. Outdoor voice, right?
Yeah, outdoor voice. That's actually a question for Sheehan. Sorry, Russ.
Okay, Xiang. Okay, Xiang. Thank you very much. Thank you. Sorry.
Is a question for Sheehan.
go for
So
it.
yeah, I'll let him take the stage. It's good to see you, man.
Yeah, good to
It's
see
nice
you.
to hear from you. Great presentation. I just have one small technical question going back to the decensoring part of the presentation. You talked about how you use like surrogate values and you calculated Kaplan-Meier curve.
Yep.
And from what I understand, the Kaplan-Meier curve involves a population of patients. Did you make that curve with just the censored patients, or was it a different subset of patients? I just didn't catch that part.
So the Kaplan-Meier curve is always about the whole population involving
Okay.
both uncensored and censored part. And yeah, that sounds
So you used both
Yeah,
to grab those surrogate values. Okay.
Yeah.
Great. That was my only question. Great presentation.
We're being kicked out, unfortunately, but I'm around. And also, if anyone's interested in medical applications, there's a meeting coming up at 4:30, a few blocks from here. But I'm here for questions.
Yeah.
So people want to just come up, I guess, because no, you ask your question.
Yeah,
They're not going to keep ask your questions. They're not going to kick us out.
back.
What are they going to do? I mean,
Hey,
eventually they get pulled off. Yeah, go for it.
very interesting talk. I just wanted to ask a quick question about what about the causal effects of this covariates? Like, are we gonna certify like their effects? I'm just saying that if one of these like covariate effect have a causal effect on the other effect, how we are gonna evaluate like the end like effect of one covariate, or if they are like just like having a relationship between these covariates.
You want to take it?
Well, first, yeah, nothing I talked about how the word causality. I'm very interested in causal issues, but this doesn't involve that.
Yeah, I would just like
Yeah.
curious
Now,
about it.
now, in terms of, I mentioned Cox as a very simplistic model, which assumes independence, which is a very strong assumption, and our empirical evidence shows it's not a very good assumption. It doesn't work very well in many cases. Is that because of causality or just correlation? I don't really care. Now, if you want, but there are other studies I've done, which is trying to look at, for example, the breast cancer analysis, saying, here's breast cancer, here's things a patient could adjust, more exercise or lose weight. We can imagine a model which tried to say, here's a model we learned with you losing weight, here's a model with you gaining weight. Look at that. This is a true one. This is a counterfactual one. We can guess what would happen, but maybe if you lose weight, you start smoking and it ends up being even worse, right? So again, all these causality are things that I think is really important. We didn't talk about it all here, but I'm very interested in it.